Assalamualaikum dear students, I hope you are fine and in the best condition of your health. So today we will discuss about dehydrogenation reaction, and specifically the dehydrogenation reaction that will involve in the formation of that will result in the formation of carbon-carbon double bond. So before we go to our topic, let's discuss something that's very important and you should know about that. So always remember, whenever you carry out redox reaction, so whenever a chemical species is oxidized, always remember that some other species is also going to be reduced. And since in organic reactions we always use inorganic reagents, so normally when an organic species is oxidized, some inorganic species is also reduced. Similarly, if we carry out the reduction of an organic compound, the inorganic reagent we used is also oxidized. Right? So the oxidation and reduction reaction, which are shortly described as redox reaction, they go in parallel. So one species is oxidized and other is reduced. Also, an important thing that you should know about the redox reaction is that the redox reaction involves the actual overall transfer of electrons from one species to another. Right? The species which is oxidized always loses electrons, and the species which is reduced gains the electron which was lost by the species which was oxidized. Right? So also sometimes it becomes confusing that how do we know how the electrons flow. Right? So if you are if you have trouble remembering that how electrons flow in oxidation and reduction reactions, so there is a hint. Right? So this hint helped me, so I thought it might be helpful for you at all as well. So the word oxidation starts with letter O, right? And the second letter of positive is also O. So always remember that when things become positive, it means they are oxidized, right? And what do we mean by oxidized? It means it loses electron. So whenever a species loses electron, it becomes positive, and when a species becomes positive, it means it's oxidized. Right? Similarly, both reduction and negative have a second word E, right? So they have the same E. It means that when things get negative, they are reduced. You know that when things get negative, it means they get electron. So when a species gets electron, it becomes negative, and when it becomes negative, it means it's reduced. So just by seeing the sign, just by watching the sign, the charge on any species, you can tell whether it's reduced or oxidized. So if a species has a positive charge, it means it has been oxidized, and when a species has a negative charge, it means it has been reduced. Right? Another important thing is that when you are studying about the organic redox reaction, the electron transfer is usually difficult to see in the organic reactant and organic product. For example, consider that we convert a secondary alcohol to a ketone, right? So the conversion of an alcohol to ketone is the oxidation process, but by just watching the reactant product, we don't know whether alcohol has been oxidized or ketone has been oxidized, or which has given the electron, which has lost the electrons. So we cannot see it obviously whether electron transfer is taking place or not. However, these electron transfer are visible in the inorganic reagents and products of the redox reaction. Right? So we just use this common concept that in organic reactions it becomes difficult to predict that how the electrons are flowing, but the charges are visible in the inorganic reagent. So just by watching the sign, just by observing the sign of the charge in an inorganic reagent, we can predict whether it's getting oxidized or not. So for example, we take the oxidation of alcohol to ketone, and we know that to carry out this conversion, the reagent we use is normally a chromic compound, and chromium is in +6 oxidation state. So during this reaction, when the alcohol is being converted into the ketone, chromium is reduced from chromium 6 to chromium 3, right? So the positive charge has decreased in going from 6 to 3. It means the chromium has gained electrons. Since chromium has gained electrons, which is the reagent, and the product will be definitely oxidized, right? So since chromium has gained electrons, it means it has been reduced. So since chromium is reduced, the other thing that was our product that has been oxidized, right? So in this way, if it becomes confusing for you to know whether organic compound is oxidized or not, just see or just observe the inorganic reagent. If the inorganic reagent is oxidized, it means the organic compound has been reduced. Or if the inorganic compound is reduced, it means the organic compound. If the inorganic compound is reduced, it means that the organic compound has been oxidized. So in this way, we can decide whether the organic compound has been reduced or not. Right. Another important thing, which is very important in the redox reactions, is the oxidation level of organic compound. Right, again, it's not easy to check whether organic compound has what oxidation state is positive or it's negative oxidation state. So this table given here will be helpful for you to decide what's the oxidation state for the carbon. Right. So when a thing is more reduced, it has a negative oxidation state. And always remember, whenever an organic compound is becoming reduced means gaining electrons. So gaining electron gives a negative sign, right? So more the negative sign it has, the more it will be reduced. Similarly, if an organic compound loses electrons, right? So you know that losing electron gains positive charge, and if a thing has a positive charge, it means it has oxidized. So just see this table. So we have zero oxidation state, and just see below. So in zero oxidation state, we have alkenes, we have alcohols. So it means the alkenes and alcohols, they have zero oxidation state, right? So oxidation state of alcohol and alkenes is the same, right? So let's go on towards the more positive side. So here we have carbonyl compound. So carbonyl compound, if it's an aldehyde, it has oxidation state of +1, while if a carbonyl compound has an oxidation is a ketone, its oxidation state is +2. Similarly, if a carbonyl compound is carboxylic acid, then its oxidation state is +3. Also, if you see below, if you have a carboxylic acid derivative, whether it may be alcohol, it may be carboxylic acid halide or carboxylic acid anhydride, all of these have +3 oxidation state. Now let's go on the more reduced side. So if you see here, we have alkene, but that alkene is disubstituted here. Similarly, alcohol. So this alcohol, which is primary alcohol, has oxidation state of -1. Right. Similarly, if you see below, here we have alkyl halides. So Z can be anything. So in general, it's alkyl halide, or it can be an amine. Just replace this Z with anything else. Right. So all of these compounds have oxidation state of -1. Now we go to this alkene with 2 carbons. Then in that case, if you have long chain of alkenes, these have oxidation state of -2. And suppose we have simplest alkanes like that one, which are unsubstituted, then in that case the oxidation state will be -3. So you can see that the alkenes, the simplest alkanes, have most reduced form. They are the most reduced form with oxidation state of -3. So it's important not to know about the numbers of the oxidations. It's not important to remember whether this is the oxidation state of that carbon or this is not the oxidation state of that carbon, but just keep this table in mind, because it helps you to understand whether if we convert an alcohol into aldehyde, so whether we are oxidizing or reducing. So you can see that from the table that if you have an alcohol, so alcohol has 0 oxidation state, right? So if you have a secondary alcohol, it's a 0 oxidation state, but if you have primary alcohol, it has -1 oxidation state. But the aldehyde has +1 oxidation state, right? So you know that when you have converted an alcohol to aldehyde, it means you have reduced, you have oxidized the alcohol, right? So alcohol upon oxidation is converted into aldehyde, and aldehyde upon reduction is converted into alcohol. So if you remember this table, it will be easier for you to know whether the compound you are studying has been oxidized or has been reduced. Right. So organic chemistry involves conversion of small functional groups into one another, and just instead of remembering all the numbers, here is another shortcut if you want to know about that and if you are getting confused about the table. So we can predict the oxidation level of an organic compound by checking the number of hydrogens attached to it, right? So if an organic compound has a higher number of hydrogens attached to it, it's highly reduced. However, if you just go on decreasing the number of hydrogens, then the decrease in number of hydrogens will make the organic compound more oxidized. So just see that at the most left corner we have methane. So methane has 4 hydrogens, right? So with 4 hydrogens, it's the most reduced form. Then as we go towards this right side, we have by the end carbon dioxide. So carbon dioxide is the most oxidized form because it has no hydrogen, right? So by seeing the number of hydrogens, you can predict whether the oxidation state is highly oxidized or highly reduced or whatever. So this is a comparative way to predict the oxidation level of an organic compound. Right. Similarly, if you have organic compound with 2 or more than 2 carbons, then in that case we can also see that. So here, so with ethane molecule with 2 carbons, this is the most reduced form because it has maximum number of hydrogens attached. Then come the alcohol and the alkene. So always remember that alcohol and alkene, they both have the same oxidation number, right? They have the both same oxidation state, right? And similarly we have aldehyde, and we have here is an epoxide. So aldehyde and epoxide, these both have also the same oxidation state. And carboxylic acid, this is the most oxidized form, right? So as mentioned earlier, that alcohols and alkenes, they are considered to be in the same oxidation state. So if you just review the basic organic reactions, you know that alcohol and alkenes can be easily interconverted by each other. So in alkenes, if you add water, then you get alcohol, and in alcohols, if you eliminate water, you get the alkenes, right? So if you oxidize the alcohol, right, you get alkene, and if you just reduce the alkene, you get the alcohol, right? So if you oxidize one, you get the other, and if you reduce one, you get the other one. So overall, there is no oxidation state, right? So you cannot just simply carry out this oxidation or that reduction. So it's very easy to convert one functional group to another, because if the reagent added to alkene, so part of reagent oxidizes the carbon, the other carbon gets reduced. Similarly, if you are treating the alcohol with a reagent, so if part of reagent oxidizes the alcohol, the other part will reduce the alcohol as well. So overall, there is no change in oxidation state of these molecules. You can simply interconvert them without change in oxidation state. However, when you convert an alcohol both to aldehyde, so there is a change in oxidation state, right? So there will be change in oxidation state of the reagent, and there will be change in oxidation state of the reactant and product as well. But when you convert this alcohol into alkene or alkene into alcohol, so there is no change in oxidation state overall, right? So considering you have just what we mean by the redox reactions, let's go to our topic. So oxidation of a carbon atom in organic compounds, it may involve one or more of these following changes. So whenever there is increase in the number of multiple bonds of the carbon, it means that organic compound has been oxidized. In case if an oxygen has been added to carbon, it means the organic compound has been oxidized. Or in case if a hydrogen on carbon has been replaced by oxygen, it means the organic compound has been oxidized, right? So in German we say that organic compound is actually the gain of oxygen, or oxidation is actually the gain of oxygen or loss of hydrogen, right? So today in our lecture we'll consider the first change, that is increase in number of multiple bonds on the carbon, right? So the topic we are going to discuss is about dehydrogenation. Right, so dehydrogenation means, D means removal, hydrogenation means hydrogen. So if you remove two hydrogen atoms from a molecule, that means you have removed a hydrogen molecule. Right, so two atoms of hydrogen will form a hydrogen molecule, right? So whenever there is elimination of two hydrogen atoms from molecule, the reaction is said to be dehydrogenation reaction. So in this reaction, in this lecture, we will consider the dehydrogenation reactions that will result in formation of carbon-carbon double bond, right? So dehydrogenation reaction is actually reverse of hydrogenation. Hydrogenation means addition of hydrogen, so dehydrogenation is the reverse of hydrogenation. So dehydrogenation will involve the removal of two hydrogen atoms from the molecule, right? So dehydrogenation reaction is very important because it converts alkanes into alkenes or olefins. Right, so why it's important? Because you know that alkanes don't react at all, or they're relatively inert and have low value, but somehow if we can convert alkanes into alkenes, so alkenes are reactive, and since they're reactive we can make much more things from alkenes, not from alkanes, right? So alkanes are of very little use to us, but alkenes are more valuable from synthetic chemistry point of view. So normally when we have to carry out the dehydrogenation reactions, we have to use high energy in the form of normally heat. So we require temperatures of 500 and above and high pressures as well, right? So dehydrogenation is useful in converting saturated fats to unsaturated fats. So some enzymes are also used which catalyze the dehydrogenation reactions as well. So the enzymes which catalyze the dehydrogenation reactions, such enzymes are called dehydrogenase enzymes. So we'll not discuss about the enzymatic dehydrogenation reaction. We'll consider the common reagents which are used to carry out this hydrogenation process. So another thing that's important, that never confuse about dehydrogenation and dehydration, right? So both words are very similar, right? So hydrogenation and dehydrogenation, similarly hydration and dehydration. So hydrogenation, dehydrogenation means addition of hydrogen or removal of hydrogen respectively. Hydration and dehydration means to add a water molecule or to remove a water molecule, right? So remember, hydration means water, right? So if you add or remove water, it means hydration or dehydration. But if you add or remove hydrogen molecule, that it means you are considering the hydrogenation and dehydrogenation reaction. Also, hydration or dehydration, that's not a redox reaction, right? That's not a redox reaction, while hydrogenation and dehydrogenation, that's a redox reaction. So when a carbon atom in an organic compound loses a bond to hydrogen, right, and forms a new bond to some heteroatom or to another carbon, the organic compound, it has been said to be dehydrogenated or oxidized. Right, so I again repeat that. When a carbon atom in an organic compound loses a bond with the hydrogen and makes a new bond to some heteroatom or to another carbon, then we say that compound has been dehydrogenated or it has been oxidized. So the classes of reactions that are concerned with dehydrogenation process, these involve aromatization, which has been discussed in the previous lecture, dehydrogenation of paraffins. So paraffins, as you know, are the alkenes, right? So since alkenes have little or no affinity, they are least reactive, therefore alkenes are also known as paraffins. So in today's lecture we'll consider the dehydrogenation of alkenes, right? And further, another class of this dehydrogenation reactions is the oxidation of alcohols to ketone or aldehydes. And then lastly, we will consider the hydrogenation of amines. Right, so let's consider about the dehydrogenation of paraffins. Right, so paraffins or alkanes, they can be converted into double bond or alkenes either in the presence of heat or in the presence of catalyst. Right, so if you can see that the entropy for this reaction is positive, enthalpy for this reaction is positive. Right, so enthalpy positive means that system has gained energy. Right, so if you know the basic chemistry, basic physical chemistry, you know that whenever a system has gained energy, it becomes unstable. So since the enthalpy of the system is increasing, it means the reaction is unfavorable. It's not favored by enthalpy. But if you see the entropy is positive. So since the entropy change is positive, means entropy is increasing, so the reaction will be favored overall. So it's important for you to know that the dehydrogenation reactions are not favored by enthalpy, but they are favored by entropy. So you can also simplify the entropy factor by that. When the number of product molecules is higher than number of reactant molecules, we say that entropy has increased. So in dehydrogenation reaction, since we have one reactant and we have two products, since products are more than reactants, so we say that entropy has increased. So if you don't have the value of entropy, just by seeing the equation you can predict whether the entropy has increased or not. So in dehydrogenation reaction, the entropy change is positive. So another thing which is very important for you to know is that dehydrogenation is of two types: oxidative dehydrogenation and non-oxidative dehydrogenation reactions. So firstly, we'll discuss about the non-oxidative dehydrogenation reaction. So these are actually series of reversible reaction when two reactants react to form two products only, and these two products again form two products, and so on. So there is no loss of carbon, so no carbon goes out of the reaction as well. So number of atoms remain the same. Right, so number of atoms, number of molecules in the reactant and the number of molecules in the product, they are same. Right, that's important for you to know. Right, in non-oxidative process, the number of products and number of reactants is the same. Since the number of product and number of reactant is the same, it means there is no change in entropy. Right, so for a reaction to be spontaneous, for a reaction to be favored, it's important that entropy should increase. But in this process, the entropy is remaining the same. So this reaction, this non-oxidative process, is not favored by entropy. However, this is favored by enthalpy. Right, so these non-oxidation reactions, these do occur, but they are not favored by entropy, but they are favored by enthalpy. On the other hand, the oxidative dehydrogenation reaction, shortly also known as ODH, they are favored thermodynamically because one reactant results in formation of large number of products, right, because of over-oxidation state. So because of over-oxidation, we get a large number of products. So although reaction is favored by entropy, but it's not feasible, it's not synthetically useful, because the formation of so much number of undesired side product or secondary products makes it more tedious task, because we have to separate all of these reactants, products one by one. Also, the desired product is obtained in very, very low quantity. Right, so oxidative process, although that's favored by entropy and enthalpy, but because of the number of side product or the undesired products, so this is not of much synthetic utility. It's not very much important. So normally we have, when we have to carry out the dehydrogenation of paraffins, different reagents which are used. They involve normally the currently industrial alkane dehydrogenation catalysts involve the use of mesoporous chromic oxide, aluminum oxide, or we may use platinum and palladium, or we may use chromium based compounds. Right? So if you are going to use alkane dehydrogenation, so the non-oxidative process are highly endothermic process, so they are important. However, since they use very high amount of energy, so maintaining this high temperature is not possible in the laboratory scale. So lastly, we have autothermal and oxidative alkane dehydrogenation strategies. So these are still under development and require large number of inputs. So we will consider about which type of reagents or conditions are normally used. So firstly, we will consider the mechanism dehydrogenation reactions when we use platinum, palladium, nickel, or chromium oxides, right? So in almost all cases, the mechanism is almost the same. So here we have metal surface, right? So here we have shown just platinum. However, you may use here palladium or nickel, right? The first step is that the alkane gets attached with the surface of the metal, which is our heterogeneous catalyst. So whatever be the process, it's always well understood that first step in this dehydrogenation reaction is the CH activation, right? So metal tends to form a bond with the carbon of the alkane, and the hydrogen gets shifted to other metal like this, right? So then there is creation of a carbon-carbon double bond, and when the formation of double bond is complete, the alkene detaches itself, and the metal also loses the two hydrogen atoms in the form of hydrogen molecule, like this one. So this is the mechanism for formation of alkene by means of metals such as platinum, palladium, or nickel. However, if you are using chromic oxide, CrO3, so this is chromic oxide. So if you see, that first step is that the chromium gets bound to the carbon, right, and the proton gets shifted to the oxygen of chromium here, right? Then the next step, there is formation of a double bond, and once the double bond formation has been completed, see, then the second proton also gets shifted to chromium, and here we have two hydrogens. So these hydrogens remain bonded to the chromium. If that's the difference. In case of palladium, the hydrogen has been eliminated and it's been lost, while in case of the chromium, if we are using chromium oxide as a catalyst in this reaction, then in that case these hydrogens remain bonded to chromium. They are not lost as hydrogen gas. So normally these are used for converting the alkanes into alkenes. So this is the non-oxidative route. The reaction is reversible. You may say that alkanes get converted to alkene, and the reaction which is reverse is also possible, right? This is non-oxidative route. But in case of selective hydrogen combustion, that's coupled with non-oxidative route. So here what we do is that, so the problem is here that we are using oxygen, right? So this hydrogen gas which is produced, when it reacts with oxygen, that forms water. Alright, so if you remember the Le Chatelier principle, you know that if we somehow remove one of the products, then we can shift the equilibrium to the right side. Right, so in selective hydrogen combustion coupled non-oxidative routes, what we do is that the hydrogen that's produced is removed. And how it's removed is removed by reacting it with water, with oxygen. So this hydrogen gets converted into water. So this water is removed by different means, right? So since we are removing this hydrogen from the reaction mixture, so equilibrium is shifted towards the right side. So if you see about these two reaction arrows, reversible arrow reaction, although it's reversible, but you can see that forward reaction is much more favored. However, the reverse reaction is not favored at all. So the small length of this short arrow indicates that reverse reaction is not much favored. Then this is the oxidative route. Here you can see that we have two reactants and we get the two products. So this is the oxidation. So two hydrogens which are removed, they react with water and react with oxygen to form water. And here we have the alkene, which is our product. Okay, so thermal cracking is a very common method. It's very old method, and it's still being used. So normally this method is used in the petroleum cracking, right? So cracking is given the name, which means to break up large hydrocarbon into smaller hydrocarbon, and the smaller hydrocarbons that are obtained, they are more useful, right? So thermal cracking is normally achieved by using high pressure and high temperature, and normally catalysts are not used. When we use catalysts, then we have to use lower temperatures and lower pressure, right? So in case if you are using a catalyst, then in that case the cracking is called catalytic cracking, right? And if you are not using any catalyst, then in that case this is called thermal cracking. So this is the difference between thermal cracking and catalytic cracking. In case of catalytic cracking or catalytic combustion, so we make use of catalyst at low temperature and low pressures. But if you are not using any catalyst, then in that case the reaction of dehydrogenation is called thermal cracking. So thermal cracking is not of much importance from synthetic chemistry point of view. The reason being that because there is no simple reaction, there is no single reaction that's happening in the cracker. So when you put a hydrocarbon molecule into the cracker, it is broken down in random ways to give a mixture of products. So a mixture of smaller hydrocarbons are obtained, and among these hydrocarbons which are obtained, some have carbon-carbon double bond, some don't have carbon-carbon double bond. So since our interest is in the alkenes that are obtained, so the alkenes that's obtained have low yield because of formation of large number of other products, right? So this thermal cracking is not of much use to us. So in thermal cracking, as I mentioned earlier, that we maintain high pressures and high temperature. So the temperature range is up to 450 to 750 degrees C. So this is high pressure, high temperature, and the pressure which is used is normally up to 70 atmosphere. Right, so these conditions are very harsh, and under these conditions the large hydrocarbons are broken down into smaller hydrocarbons. So here you can see about an example. So here ETC means it can have further carbons as well. It has not been specified, but just we have showed these two electrons because we are showing that this bond has been broken. So since this bond can be broken, or the bond between carbon-carbon from this side, or the carbon-hydrogen bonds can be broken, anything can be broken. So there is no specification in the thermal cracking. So here we are showing that this bond between this carbon-carbon, these two electrons are shown in red color. So this bond is broken under thermal cracking conditions, and this cleavage of bond, this is called homolytic cleavage. Right, so what are homolytic cleavage? Homolytic cleavage is a cleavage in which after bond breaking, each of the atoms get one electron. Right, so this electron will get one electron, and this atom will get one electron. So each of these carbons will get one electron each. So a species with unpaired electron is called free radical. So the thermal cracking process involves a free radical process. Right, so this is a free radical process, and since free radicals are very rapidly reacting, so the rate of formation of thermally cracked product is very higher. Right, so in case if you are considering the catalytic cracking, then catalytic cracking result in formation of cation and anions. So these catalytic cracking involves formation of charged intermediates, whereas the thermal cracking involves formation of free radicals. Right, so carbon-carbon bonds are broken, and each carbon ends with electron pair, so free radicals are formed. So these free radicals are very non-selective in their reactions, so they can end up in any way. So because since the free radicals are formed and free radical reactions are not selective, so the thermal cracking result in formation of large number of products. As we don't get only one product, suppose we are starting with a pentane molecule, so the pentane will result in formation of methane, it can result in formation of ethane, propane, butane, it can result in formation of suppose ethene, propene, butane, right? It can formation, and it also may result in formation of pentane as well. So in thermal cracking, we not only break the carbon-carbon bonds, but also carbon-hydrogen bond as well, right? So we get a large number of products. So since we get a large number of products, so the thermal cracking is important on petrochemical scale. But when you are considering an organic chemistry strategy, so these reactions are not of much use, right? So far we have discussed about the use of metals such as palladium, platinum, nickel, or we have used chromic oxide for dehydrogenation of alkanes, right? So dehydrogenation of alkanes is very important because, as mentioned earlier, alkanes are not of much use because of their least reactivity, but once we get a double bond from the alkane, once we convert the alkane into alkene, then the alkenes are useful product because they can be converted into other functional groups with much ease, right? So not much common reagents are available in these reactions, and whatever the reagents are available, they are not selective, right? So what we mean by selectivity here? Selectivity means, suppose that we have a butane. We have a butane molecule, a straight chain molecule, and suppose that we want to create a double bond between carbon number 2 and carbon number 3, right? But when we carry out the dehydrogenation under these conditions, we not only get the double bond between carbon number 2 and carbon number 3, but we will also get a double bond between carbon number 1 and carbon number 2. Alright, so there is no selectivity in the dehydrogenation reactions we have observed so far, we have studied so far. But these chemical reagents are much cheaper, they are very much economical. So instead of going towards much more expensive reagents, it's much favored to carry out the dehydrogenation reactions of alkanes by using either cheaper catalyst or by using thermal cracking, because in thermal cracking all you have to do is to apply high temperature and high pressure, so we don't have to add anything else, right? But when you are designing a product, and when you are designing a product with a desired carbon-carbon double bond at specified position, then in that case you are left with no other reason but to go for some selective catalyst, right? So what we mean by selective catalyst or selective reagent? So a selective reagent will bring about a carbon-carbon double bond at the position, or preferably at the position which is desired to us, right? So let's consider about some selective dehydrogenation reagent. So before going to that dehydrogenation reactions, so it is important to note that these conditions are only applicable for lower alkanes. So if you go for the alkanes with higher molecular weight or more complicated alkanes, then in that case the selective dehydrogenation is not much used, right? So one of the most commonly used selective dehydrogenation reagent for lower alkane is PSCOP, pincer iridium catalyst, right? So this catalyst is shown here, right? So why it's called pincer? Because it's just like a pincer. So what we mean by pincer means in Urdu we call it नेज़ा. जैसे नेज़ा होता है मछली को मारने के लिए, ये भी बिल्कुल नेज़े की तरह है. Just consider this middle point. ये सेंटर वाला जो कार्बन है इसको आप इमेजिन करें, तो you can just imagine it as नेज़ा, just pincer. So what is meant by PSCOP? So if you just check that out, this is P, S means phosphorus, sulfur, then we have carbon here, central carbon, then O, and then P. So these are the atoms, these are the heteroatoms which are somehow connected to this iridium, right? So that's why this catalyst is called PSCOP, iridium catalyst. And it's called pincer because its shape is just like a pencil, right? So this catalyst is useful for dehydrogenation of linear alkanes as well as cyclic alkanes as well, but limitation is that it is only valuable for alkanes, whether cyclic or linear, which are lower alkanes. So you cannot use complicated alkanes for these reactions, right? So this hydrogenation reaction has the advantage that it is mild. It is carried out under mild conditions, and it is highly regioselective. So if you want to bring a double bond at a certain position, desired position, that will give you a double bond at that desired position. So that's a regioselective, and it's useful for alpha olefin formation, right? So you can also use it for creating a double bond between carbon-carbon in heterocyclic system, just for this system. So if you have a carbon-carbon single bond here, and if you use this BSUP pincer iridium catalyst, so you can bring a double bond here between carbon-carbon, right? So this is all about dehydrogenation reactions. So we have discussed about what we mean by oxidation reactions, what are redox reactions, and how we can just predict about the oxidation state of an organic compound. Then we have seen how we can carry out the dehydrogenation of alkanes in order to create a carbon-carbon double bond, right? I hope that's all fine. You should know about the selectivity of dehydrogenation reactions as well, also the concept of oxidative dehydrogenation and non-oxidative dehydrogenation. That's important for you to know. So that's all for today. Thank you very much.